Here is a question from JEST 2024 where we are given an ideal gas which is undergoing a sequence of processes. We have to identify the correct relation between initial pressure and final pressure of the gas. So the first process the ideal gas undergoes is a reversible adiabatic expansion that doubles its volume. So let's say initial volume is V1 is equal to V. Then after the first process V2 is equal to 2V because it is given that the volume doubles. And in the case of adiabatic expansion, we have the relation PV raised to gamma is equal to constant. In the case of adiabatic process, we have PV raised to gamma is equal to constant. Therefore, we can write P1 V1 raised to gamma is equal to P2 V2 raised to gamma. From here, we have P2 is equal to P1 V2 divided by V1 divided by V2 raised to gamma. This implies P2 is equal to P1 times V1 is V and V2 is 2V raised to gamma, which is equal to P1 1 by 2 raised to gamma. So this is the pressure after the first process. Now let's go to second process. In the second process, we have a reversible isothermal compression that restores its original volume. For isothermal process, PV is equal to constant because we have ideal gas. For reversible ideal gas, PV is equal to nRT, and N, we are not changing the number of moles, so N is constant, and R is universal gas constant, T is constant in isothermal process, so therefore PV is equal to constant, which implies P2 V2 is equal to, let's say P3 and V3 are the volume and pressure and volume after the second process. This implies P3 is equal to P2 V2 divided by V3, which is equal to P2 is P1 into 1 by 2 raised to gamma V2 is equal to 2V divided by V3. Here it is given that after the process it restores its original volume, so V3 is equal to V, which means P3 is equal to P1 1 by 2 raised to gamma. So after the second process, we have V3 is equal to V and P3 is equal to 2P1 into 1 by 2 raised to gamma. Now in the third process, we have a reversible isothermal expansion that doubles its volume. So volume is doubled, which means V4 is equal to 2V, and in the case of isothermal process, we have PV is equal to constant, which means P4 V4 is equal to P3 V3. This implies P4 is equal to P3 V3 divided by V4, which is equal to P3 is 2P1 1 by 2 raised to gamma V3 is V, and V4 is 2V. 2 cancels, V cancels. Therefore we have P4 is equal to P1 into 1 by 2 raised to gamma. Now after the third process, we have pressure P4 is equal to P1 into 1 by 2 raised to gamma, and V4 is equal to 2V. Now in the final process, so V4 is 2V and P4 is equal to P1 into 1 by 2 raised to gamma. In the final process, we have a reversible adiabatic compression that restores its original volume. So V5 is restores its original volume, means V5 is V, and P5 is equal to, in the adiabatic case, PV raised to gamma is equal to constant. Therefore P5 into V5 raised to gamma is equal to P4 into V4 raised to gamma. This implies P5 is equal to P4 into V4 divided by V5 raised to gamma, which is equal to P1 into 1 by 2 raised to gamma, this is P4, times V4 is 2V divided by V5 is V raised to gamma. So this is equal to P1 into 1 by 2 raised to gamma, 2 raised to gamma. This is equal to P1 into 2 by 2 raised to gamma, which is equal to P1. Therefore we have P5 is equal to P1, which means final pressure is equal to initial pressure. So the correct answer here is option A. There is no need to do this much calculation to solve this problem, because this is a cyclic process. We have adiabatic expansion, and then there is adiabatic compression. We have isothermal compression, and then there is isothermal expansion. So this is a cyclic process, and in the cyclic process the net change in state functions are 0. So in cyclic process we have internal energy is equal to, internal energy change is 0, entropy of the system, change in entropy of the system is 0, change in pressure of the system is 0, change in volume of the system is 0. This is a property of a cyclic process, that the net change in state functions are 0.